Hello guys, thank you for joining me today. In this video, we are going to start a new module talking about the axial load and deformation. We learned previously that we have something called axial stress, and this axial stress is a kind of normal stress. But this axial stress is coming from axial force. And the axial stress will cause change in the length of the body. If we have compressive strength, we will have contraction. We will have contraction. The length of the body or the member will be shorter. If we have tensile stress, which is coming from tension force, that means the body to become longer. The length will be longer. And keep in your mind, the axial stress equal the applied force, the axial force divided by the cross-section area. The cross-section area. And keep in your mind, if your force is tension, that means the stress will be tensile stress. And it will be positive. If the applied force is compression, that means the created stress will be compressive stress, and it will be negative. And keep in your mind, if we have tensile stress, we will have elongation. We will have stretch in the length of the member. If we have compressive stress, we will have contraction. We will have shortening in the length of the member. That makes sense? We have few examples here to explain this. Excuse me. The thrust bearing is subjected to the loads shown. Determine the normal stress developed in the cross sections B, C, and D. So let's start to figure out the stress at point B. It's a very important. Sigma at B equal the applied force divided by the cross-section area at point B. If you would like to figure out the applied force at point B, I'm gonna do cut. I have two options. I can work with the upper part or the lower part. It's up to you. So I can use this part, which is very easy. So this part looks like this. And I did cut here at point B. And we have applied force at this end, 500 Newton. To make equilibrium and to apply summation F of y equals 0, we must have another force at this section or at this cut equal also 500 Newton to make sure we have equilibrium from engineering mechanics. So at your cut at point B, we have a force pushing the cross section. So this force will cause compression. That makes sense. So the applied force will be negative 500 Newton, negative Y, because it's compression, divided by the cross-section area, the diameter of the part at point B with 65 millimeters. So the area will be pi divided 4 times 65 millimeter square. If you divided the two numbers, 500 divided by pi divided 4 times 65 square, the stress will be negative 0.15 megapascal. Newton by millimeter square is called megapascal. Negative because it's a compressive stress. That makes sense? For point C, stress at point C equal force divided by area. Let's see what we have at point C. I will do cut at point C. Then you can decide which part or which side I'm gonna use, the upper part or the lower part. It's up to you. Both of them will give you the same answer. So I will use the upper part. We have this part, and I did cut in this part at point C. Here is point C. What do you have on the upper part? This one, I have the applied force here, 500 Newton. Do you have anything else? No, we don't have anything else on this part, the upper part. We don't have anything else except this force. So if you apply summation F of phi equals 0 for a chromium, we must have a force here in this direction to make a chromium equal 500 Newton. This force in this direction related to this section is pushing the part at point C. So this force which is pushing, that means it will cause compression. So the stress equal negative 500 Newton divided by the cross-section area. The diameter of this part at point C has a diameter 140. So the area will be pi divided 4 times 140 square. So the stress will be negative 500 divided by pi divided 4 times 140 square equal negative 0.032 megapascal. We are looking for the stress at point D. So stress at point D. Sigma at D equal the applied force divided by area at D. So what should I do? I will do cut at point D. Be careful. If you did cut at point D, we have two options. We can use the lower part, this little part, or this upper part. It's up to you. For me, I'm gonna use the lower part, which is this one. So I have this cut, and I have this part at point D. Keep in your mind, I'm gonna use this part with everything you have. We have only 200 Newton, like this. Nothing else. Nothing else on this part after you did cut at D. So if you apply summation f of y equals 0 to make sure we have a chromium, we must have a force like this, equal to 100 Newton. This force with this direction related to this part that you draw is pushing. So it will cause compression also. It's pushing. So it will cause compression. And the diameter of this part is 100 millimeter. So your force will be negative 200 Newton compression. The area will be pi divided 4 times 100 square. So the value will be negative 200 divided by pi divided 4 times 100 square equal negative 0.025 megapascal. Does that make sense? So to solve this kind of problem, we have two steps. The first step, engineering mechanics, how much force at your cut, and this force is pushing or pulling, tension or compression. Then the stress will equal the force divided by the cross-section area. We have another example. For the shown rod, we need to determine the axial stress in parts AB and the part BC. So let's start with the first part AB. Keep in your mind, the axial stress in part AB will equal the applied force in this part divided by the cross-section area of this part. To figure out the applied force in this part, I will do cut at any point inside this part. Actually, we have two options. You can use the upper part, but we must have, or we must figure out the reactions at support A. We don't have these reactions, so I do recommend to use the lower part. So I'm gonna use the lower part. Actually, both of them will give you the same answer, but the upper part, I don't know how much reactions at this support A. So I'm gonna use the lower part. So the lower part looks like this. We have this part, and I did cut here, and we have this part. This is point B, this is point C. We have a force here, 60 kilonewton, and we have two forces here, 125 kilonewton, 125 kilonewton, and that's it. So if you apply summation F of y equals 0, if we apply summation F of y equals 0, I believe 100% we will have a force coming down to make equilibrium. This one is 60 down. This one and this one 250 up. So I believe with this one will coming down 190 kilonewton. So if you apply summation F of y equals 0, so 190 plus 60 will give you 250, which is in equilibrium with these two forces. So at your cut in part AB, this force 190 is pushing the section, the cut. So your force will be negative 190. I will multiply it by 1000 to be in Newton. What is the cross-section area at your cut? The diameter at this cut equal 50 millimeters. So the area will be pi divided 4 times 50 millimeter square. So the stress will be compressive stress, negative. How much? 190 times 1000 divided by divided 4 times 50 square. It will be 96.8 megapascal or Newton per millimeter square. This is for part AB. The second part BC. Your stress sigma in part BC will equal the applied force in this part divided by the cross-section area. So I will do cut in this part BC, this one. And I'm gonna use the lower part because the upper part will include reaction and I don't have these reactions. So if you used the lower part, I did cut here at C. We have here C and I did cut here. So we have a force here, 60 kilonewton. Very simple. If you apply summation F of y equals 0, we must have a force coming up equal 60 kilonewton also. So we have equilibrium. Looks like this force related to this cut, it's pulling. So we will have tension. That means the applied force will be positive 60 kilonewton. I'm gonna multiply it by 1000 to be in Newton. Positive because your force is pulling. In the previous section, your force is pushing the cut. And divided by the cross-section area, the diameter of this part is 30 millimeters. So pi divided 4 times 30 millimeter square. So the stress will be positive, tensile stress, 60,000 divided by divided 4 times 30 square. It will be 84.88 megapascal or Newton per millimeter square. Keep in your mind, we decided if we have axial stress, tension, or compression, we will have change in the length of the member. So If we have applied force which is causing tension, this force will cause tensile stress, and this force will cause elongation. This elongation will equal P, the applied force, time L, the original length of the member, divided by E, Young's modulus, time A, the cross-section area of this member. The same, keep in your mind, the same, if we have this member under the effect of compression force, we will have contraction. The length of this member will be shortened by value equal delta. This delta, which is called contraction in this case, will equal the applied force B times the original length of this member L divided by the cross-section area time Young's modulus of the material of this member. That makes sense? So make sure we understand this point. The deformation that occurs in a body due to axial load or axial stress is known as axial deformation. After the axial deformation, the axis of the structure does not change. The cross-section area of the plane will remain unchanged. After the deformation, the cross-section of the structure does not rotate about the same axis. These are the assumptions that used to say the elongation or the contraction will equal PL divided by A divided by, time E. If we have many elements or many parts connected together, so we have this part with area 1 and the length L1 and P1 and the material E1. We have another part here with area 2, L2, applied force B2, and Young's modulus E2. And we have another part here, area 3, with length 3, applied force 3, Young's modulus 3. And these elements connected together, so the total elongation or the total contraction will be summation. I mean, you have to add P1 L1 divided by area 1 E1 plus P2 L2 divided by area 2 E2 plus B3 L3 divided by area 3 E3. This will give you the total elongation that can be happen in this element. Does that make sense? We have many examples covering this point. The first example is this one. For the shown rod, the diameters and the lengths of each part are shown in the figure. AB, part BC, part CD. The diameter is given and the length of each part is given. The rod is made of steel and this steel has Young's modulus equal 30,000 KSI. We need to calculate the total elongation at point D. At this point D, what is the total elongation at this end? Keep in your mind, since we have different parts, A, B, B, C, C, D, that means the total elongation at point D will equal summation for P time L divided by A time E for all of these parts. So let's start with each part one by one. For part AB, what is the length of part AB? It will equal 12 inch. What is the area of part AB? The cross-section area equal by divide 4 times 3 square. This value equal 7.1 inch square. The Young's modulus of this part is 30,000 psi. What is the force P in part AB? This is a question. To figure out the force in this part AB, I'm gonna do cut. This cut, you will have two options. The right part, this is the first option, or the left part. Both of them will give you the same answer. But for the left part, I should figure out the reactions at A. I don't have time to figure out this reaction, so I will decide to use the right part. If you use the right part, that means we have this cut. Here is point B. At point C, we have a force here, 18. At point D, we have a force here, 12. Nothing else. So I did cut in part AB. I decided to use the right part of the rod. So I have this free body diagram. If you apply summation f of x equal 0, we have a force here equal 18. We have a force here equal 12. Looks like we must have a force here in this direction equal 6 kip. We must have a force here in this direction equal 6 kip. So 6 plus 12 will be in equilibrium with 18. So the applied force in part AB will be negative. Negative means compression because this force is pushing the cross section. So it will be compression. Compression means negative 6 kip. Right now, we have everything we need to figure out the delta, the change of the length in part AB. Equal P times L divided by A times E. Only for part AB. The applied force is negative 6 kip. The length of this part, 12 inch. The area of this part, 7.1 inch square. The Young's modulus of the material of this part, 30,000. Before figuring out the total contraction, it's not elongation, it's a contraction in part AB, we need to make sure the units are consistent. This force in kip, this length in inch, this area in inch square, this E is kip per inch square, which is KSI. Looks like everything in kip and everything in inch, we are good. Keep going. So 6 times 12 divided by 7.1 times 30,000. Your elongation will be negative 0.00034 inch. This is only for part AB. I will repeat this for part BC. So, for part BC, what is the length of part BC? What is the area of part BC? What is the Young's modulus of part BC? So the length of part BC is 6 inch. What is the area of this part? The diameter of this part is 1.5 inch. So pi divide 4 times 1.5 inch square. So the area will be 1.767 inch square. Okay. 1.5 square time pi divide 4. Yes. Let me check. Yeah, we are good. What is the Young's modulus of this part? It's only the same material, so it will be 30,000 kSi. What is the force in part BC? This is the question. To figure out the force in part BC, I will do another cut in part BC. and I will use the right part. Both of them will give you the same answer if you use the left or the right. But the left, I have reactions at A because it's fixed. I don't care about this one. So I decided to use the right part. So the right part looks like this. I did cut here. And I have point C with a force in this direction and point D with a force in this direction. These forces are 12 and 18. If you apply summation f of x equals 0, we must have a force coming to this direction equals 6 kib. So 6 kib and 12 kib in the same direction will be in equilibrium with 18 kib. And this force based on this direction and your cross section or your section is pushing. Pushing means compression. Compression means -6. So I can say we will have contraction at in part BC. This contraction equal PL divided by A times E only for part BC. So the applied force in this part, -6. The length of this part is 6 inch. The cross-section area of this part, 1.767. The youngest modulus of this part is 30,000 psi. I think your unit will be consistent. The contraction will be -0.0068 inch. This one will be contraction. Negative means contraction. We still have one more part, which is part CD. So, for part CD, what is the length of part CD? What is the cross-section area of part CD? What is the youngest modulus of part CD? And what is the force in part CD? The length of part CD is 10 inch. The cross-section area of this part, the diameter is 1.5 inch. So pi divide 4 times 1.5 square. It will be 1.76 inch square. Youngest modulus will be the same material, so it will be 30,000 psi. How can I figure out the force in part CD? We learned this from engineering mechanics. It's very easy. Go ahead and make cut in part CD. And I will use the little part on my right. So if you did cut, looks like we have this part and this is your cut. At point D, we have a force here. This force equal 12 kib. If you apply summation f of x equals 0, we must have a force in this direction equal 12 kib to make a cropping. This force by this direction is pulling. Pulling means will cause tension. 12 kib. So the elongation, because this force is tension, we should expect elongation in this part. The elongation in part CD will equal PL divided by A times E. So the applied force is positive 12. The length of this part is 10 inch. The cross-section area is 1.76. The youngest modulus 30,000. I think the units are consistent, so the elongation positive will be positive 0.00227 inch elongation. So I calculated the change of length in each part, part AB, part BC, part CD. So if you would like to figure out what will happen at the end D, I have to add all of these changes together. So the change of length or the elongation or contraction, I don't know, at point D will be summation for delta in each part. So it will be delta in part AB plus delta in part BC plus delta in part CD. So the first part give you negative 0.00034. The second part give you a contraction equal negative 0.00068. The third part give you elongation positive 0.00227. Okay. So this one in inch, in inch, in inch. What will be the final answer? Make sure the final answer will be negative or positive. I don't know. Equal positive 0.00125 inch. Positive means elongation. So the final conclusion, this member will be elongated at point D by 0.00125. So calculate the total elongation at point D. This point D will be moved to this direction. How much? 0.00125 inch. Does that make sense? So how to figure out the elongation or contraction, whatever, in a rod, and this rod consisting of different parts, I have to figure out the change of the length in each part. Part AB, part BC, and part CD. Be careful about the applied force. If the force is compression, we will have negative change of the length, means contraction. If the applied force is tension, we will have positive change in the length, which is elongation. But when you add these elongations for these parts together, make sure you include the sign for each change of the length. Sometimes we have contraction, sometimes we have elongation. If the final answer is positive, we will have elongation. If the final answer is negative, we will have contraction as a final conclusion. We have one more example. In this example, we have a beam. This beam is supported at B with a support and supported at A with a steel member or steel rod. And the beam is supporting a force 100 kilonewton. And this steel rod with a diameter equal 50 millimeter and the modulus of elasticity equal to 100 gigapascal. What is the total elongation in the rod AC? This rod will be elongated, will be stretched. How much is this stretch? To solve this problem, we have two parts. The first part is the engineering mechanics part. This beam is supported at at B with a hinge. So I will have two reactions, one horizontal XB, one vertical YB. And is supported by steel rod at A, that means we will have only one reaction in this rod, R. And we have this applied force, 100 kilonewton. So the first step, we need to figure out what is the force in the steel rod, which is R. We can apply the three equilibrium equations, summation f of x equals 0, summation f of y equals 0, summation moment at point B equals 0. I'm going to use this equation only because I'm looking for R. I don't care about the reactions at B. So I don't care about these two equations. If you take moment at B, so XB will be multiplied by 0. YB will be multiplied by 0. We don't have distance. I'm gonna assume this counterclockwise is my positive. So we have positive 100 time distance 1.25 meter. This distance will be 1.25 because this distance is 0.75, so the total will be 2 meter. Minus r times the total distance is 2 meter equals 0. The only unknown, this one will and this one will be cancelled. The only unknown is r, so I can figure out the value of the reaction r. It will be 62.5 kilonewton. So this is the force in steel rod. To figure out the elongation in this steel rod, equal P L divided by AE. I think we are missing here an information is the length of this steel rod is not given, so I'm gonna assume it's 1.5 meter. This is the length of the steel rod, should be given. For the shown the applied, yeah, the length should be given. So the applied force or the tension force or the axial force in the steel rod AC equals 62.5. The length of this steel rod equal 1.5 meter. The cross-section area of this rod by divide 4 times diameter 50 millimeter square. The diameter of this steel rod equal 50. The Young's modulus equal 200 gigapascal. I think we have an issue with the units. This one in kilonewton, this one in meter, this one will be millimeter square, and this one gigapascal. So I'm gonna multiply it by 1000 to be in megapascal. Megapascal means Newton per millimeter square. So I have to multiply 62.5 by 1000 to be in Newton. I have to multiply 1.5 by 1000 to be in millimeter. So 62.5 times 1000 will be in Newton. 1.5 times 1000 will be in millimeter. This area in millimeter square. Right now 200 times 1000 will be megapascal, which is Newton per millimeter square. So looks like the units are good. So I can figure out what will be the elongation in the steel rod or the stretch in the steel rod. So 62.5 times 1000 times 1.5 times 1000 divided by divide 4 times 50 square times 200 times 1000. It will be 0.238 millimeter because I'm using millimeter in length unit. So the final elongation will be 0.238 millimeter. So to solve this kind of problem, the first step I used engineering mechanics, equilibrium equations to figure out the force in the steel rod AC. Then I used the mechanics of material, the elongation or the change in the length equal PL divided by AE. The force in this rod, I figured this out from engineering mechanics. One more example. In this example, we have assembly consists of this one and this one, a 10 millimeter diameter red brass copper rods A, B, and CD. A, B, and CD, the diameter of these rods equal 10 millimeter. And we have another rod EF with a diameter 15 millimeter. A 15 millimeter diameter stainless steel rod EF and a rig bar at G. Where is G? This red bar at G. The modulus of elasticity for red brass, the modulus of elasticity for the material here equal 101 gigapascal. And the modulus of elasticity for the stainless steel here equal 193 gigapascal. So we have two materials. This material is brass and red brass copper rod, and this one is stainless steel. If the horizontal displacement of end F, this end F, under the effect of the applied force for P, we will have elongation at point F equal 0.37 millimeter. What is the value of the applied force P? It's very easy, and keep in your mind summation of elongations in this rod and this rod and this rod will equal 0.37 millimeter. So the total elongation is given. We need to figure out the applied force. Okay, let's start with part delta in part AB, which equal the delta in part CD. Both of them will give you the same value, which equal PL divided by EA or AE. So what is the applied force in these two bars? Or each part? Each bar. This one alone. What do you think? If you did cut and you apply summation f of x, I used the right part because I don't care about the reactions at C and A. I don't know what are these reactions. So if you have this cut and we have this cut, and this is point G, and we have this part, so we have a force here for P, we have a force here P, and we have a force here P. If you apply summation f of x equals 0, I believe 100%, we will have a force in this direction, another force in this direction, P and P. So we have P, 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 4P in this direction, 4P on the other direction, so we have equilibrium. So the force in bar AB, for example, will be P. I don't know how much is this force. The length of this part is 300 millimeter. The Young's modulus of this part, 101 gigapascal. The cross-section area of this part will be pi divided 4 times 10 square. Be careful about the units. This one is gigapascal. I will multiply it by 1000 to be megapascal, which is Newton by millimeter square. This one in millimeter square, this one in millimeter, so this force will be in Newton. So the elongation in part AB will equal pi divided 4 times 10 squared will equal 0.00037P. This is the elongation in part AB. That will be the same elongation for part CD. Both of them will elongate. So this one elongated with the same value equal 0.00037P. For part EF, I will do cut here and I will use the right part. So looks like we will have a force here for P. If you apply summation f of x equals 0, we must have a force in this direction for P. This force is pulling, it will be tension. So the elongation of part EF will equal PL divided by AE. Go ahead and put your numbers. The applied force is 4P. The length of this part is 450. The cross-section area by divide 4 times 15 square. The Young's modulus of this part is 193 gigapascal. I'm gonna multiply it by 1000 to be megapascal and Newton per millimeter. We are good. So 4 times 450 divided by this value will be 0.00052 P. So keep in your mind, I would like to highlight this point here. Keep in your mind, this is the assembly. This is point D, this is point whatever, F and G, whatever. I don't care about the names. We found that this bar and this bar, both of them at the same time will move or will be elongated to this direction, 0.00037 p. And this one, in this part only, will be elongated in this direction, 0.00052 p. So the total elongation, delta total, will equal 0.00037 p plus 0.00052 p. And this total is already given in the problem, 0.37 millimeter. So I can figure out the only one unknown, which is the applied force P. It will be 4121.33 Newton or 4.121 kilonewton. This is the value of the applied force P equal 4121.33 to be applied here and to be applied here and the 4P to be applied here. So the final elongation at point F will be 0.37 millimeter.